the next session of today for paper presentation. This session focuses on fault attacks, and for this session we have two of our session chairs, Dr. Shantanu Sharkar and Dr. Mohit Gupta. During the session, when the paper will be presented, after that you can post your question on the Q&A platform, and after the session of when the break will be there, you can join to the authors directly with the Google Meet link shared in the event platform. So over to you, to the session chair. Thank you.
Yeah, can we start now? Yeah, so good afternoon, everybody. First talk is on differential fault attack on Espresso. Authors are Bhagavan Vathe, Siddharth Tiwari, Ravi Anand, Dibyendu Roy, and Shubhay Maitra. Ravi Anand will be speaker. Ravi, please start.
Thank you, sir. Good afternoon, all. I am Ravi Anand, and I'll be presenting our work Differential Fault Attack on Espresso, which is a joint work with Bhagavan Bhate, Siddharth Tiwari, Dibyendu Roy, and Shubhay Maitra. Espresso is a 5G standard cipher which is based on 256-bit NFSR and has a nonlinear filter function of degree 6. It has 14 nonlinear feedback functions. The key size of Espresso is 128 bits and has a initialization vector size of 96 bits. Espresso has an initialization round of 256 in which the key stream bits are not outputted. So our work is a differential fault attack on Espresso. So differential fault attack can be considered as a special case of differential attacks. In this case, in this model of attack, the differential fault attack, the adversary becomes more powerful than the adversary of a differential attack. In the fault attacks, the adversary is allowed to introduce a difference in the state bits or the initial states of this key stream generation phase of the cipher by injecting faults into the state after the key scheduling phase. And this difference, which is introduced in the initial state of the key stream generation phase, makes a distinguishable impact on the key stream bits. And then these the information you got from here is used to either obtain the values of the initial state or the key. There are a few assumptions that we have made in this model of attack. The first is that the adversary has the required tools for injecting the fault. Also, adversary can inject multiple faults at that exact timings that we require or the exact round at which we need. The adversary can also restart the cipher multiple times with the same key and IV. And adversary can introduce controlled number of faults. We also assume that the adversary has no knowledge of the location at which the faults has been introduced, and so we need to first locate where the faults were introduced in the initial state. So let us consider that a fault has been injected in some unknown location, say F of the state of the cipher, and the adversary has access to lambda key stream bits for every fault injected into the cipher. Then the entire process of identifying this fault can be divided into two parts, the offline phase and the online phase. In the offline phase, first of all, the adversary computes a signature, which is a vector of length lambda, which is the lambda key stream bits that we require, and corresponding to a known fault location, say F here. SF is this vector where each SIF is computed as half minus probability of ZI not equal to ZIF, where Zi is the key stream, fault-free key stream, and ZIF is the faulty key stream. That is when the fault has been injected at a known location F. As we can see from the formula above of SIF, that it will always be between minus 0.5 to 0.5, and the signature is considered to be very strong if this value, the sigma SF, is close to 1. The closer it is to 1, the easier it is to locate where the fault has been injected. Now, when in the offline phase, the adversary uses the assumption of resetting the cipher to its original state, in which the cipher is rekeyed using the same key and the IV. and then the adversary injects a fault in some unknown location, say gamma, and will record the corresponding key stream Z0 gamma, Z1 gamma to Z lambda minus 1 gamma, where this is known as the faulty key stream. Now we need this W many times such faulty key streams because W has to be large enough so that we have enough equations and to solve to solve and then derive the state of that cipher. So we repeat this process W many times, and then we have an access to W plus 1 key stream sequences, where W are faulty key stream sequences and 1 is that fault free sequence that we have. And then the adversary will compute a trail vector for each unknown fault location lambda, where it is defined as this, that d lambda is equal to half if it is equal, and it is minus half it is not if it is not equal, for all I from 0 to lambda minus 1. Now by intuition we can say that if SF matches with the trail, if the signature at certain fault matches with a trail of certain unknown location y, then that F lambda should ideally would be the correct fault location. But to find this, generally it has been assumed sometimes that this does not happen, and there are certain, we have to check for more times, and for that we use a Pearson's correlation coefficient, mu SF mu, and we compute this for each fault location. So for each lambda, which is for each gamma, the adversary will calculate this correlation between the trail at F, which we knew, and the trail that of the unknown location, fault injected at unknown, for each possible fault location F. And then the adversary will create a list of fault indices, say L gamma, sorted with the reducing correlation coefficient. That is, with the value with the highest correlation coefficient will be the topmost, and with the lowest will be the bottom. So we'll make these many tables or lists, as we say, and we have to construct W such lists because we have so many for faulty key stream. Now once that is done, the adversary will consider a set of possible fault locations, P0, row 0, row 1 to row W minus 1, where each row I is the first is the first list from Li. So row I, so say row 0 is the first element of the list L0, row 1 is the first element of the list L1. In this way we take all those the first elements or the elements with the maximum correlation from each list, and then we try to solve this system of equation involving the state weights to after solving the equations and recovering the state, the adversary finds a 2n length key stream from the state, and then it will check it with the available key stream. If it is a miss, then the adversary will repeat the solving the equations with the next best set of locations. Now for Espresso, so this was the method in which the fault the location of the fault can be found. So in case of Espresso, we found that this figure gives the signature of this Espresso, and for we can see from this table, from this plotting, that the signatures for Espresso are very good, which means that we have a very high chance of locating the fault locations easily. This shows the correlation between the trail and a signature, and as you can see here, we can see that the maximum correlation between a certain F and a certain unknown G is completely equal to the correlation between the signature at that point of that signature and the trail of exactly that fault location. This means that it was very easy to locate faults injected in Espresso. Now, what happens in the online phase while trying to, now we try to find out the state bits of Espresso, so Espresso exactly has 14 nonlinear feedback bits. Now these feedback bits will actually make the key stream bits more complicated as the rounds increases. So to tackle this, what we do is we introduce new variables in each clocking for all these 14 feedback bits. And so if you are using n key stream bits for our fault model attack, then the total number of new variables will be 14 into n. And so the total number of variables that we have will be 14n plus 256. This complete process is described in algorithm 3 of our paper. Now in the online phase, we inject some random faults in the cipher, and we generate a faulty key stream bits as we have explained it before. Now these faults are actually injected just after the key scheduling phase of the cipher. And then the equations are formed using the state differences for fault affected state. Now, as we have explained it, as I've explained it even before, that now if a fault is injected at say at a location F in the state, then this difference del xi will be 0 for all xi if they are equal, and if they are equal, but except at this fault location the difference will be 1. So we make equations relating to this, but before going that, we need to generate certain equations for all these difference of XOR, AND of 2 bits, AND of 3 bits, up to AND of 6 bits, because there is a monomial of 6 bits, the 6 of degree 6, nonlinear monomial of degree 6. So we compute this difference expression for all higher order terms up to 6 terms. And then we compute the expressions of difference feedback bits, and using the techniques that we have already explained before, which is explained in more detail in algorithm 4 of our paper, we form this differential key stream bit equations. Using this key stream bit equations, we then try to solve and derive the secret key. So our experimentation, we considered fault locations. We injected 4 fault at locations 212, 33, 155, and 3 out of the state bits which starts from 0 to 255, and these are selected randomly. This is one of those fault locations which we are saying here, and we have 200 key stream bits which took it. And the above mentioned techniques were used to derive our system of equations. Now, once the system of equations were generated, we fed this to the SAT solver, and in 400 seconds, it returned the correct set. Then, by reversing our key IV initialization process, we were able to recover this secret key. Now, this whole experiment was done in a normal laptop, which is a 8 GB RAM, 8 GB Ubuntu. And to check the correctness of our work, we also performed a simulation in the hardware, and we found that the work that the values that we obtained were correct. So in conclusion, we can say that Espresso is not completely secure against differential fault attack if all those assumptions are taken care of. And also we only required four faults into the state of the cipher after the key scheduling algorithm, and we were able to obtain the secret key in a practical time. Thank you.
Thank you, Ravi. Any question?
Ravi, am I audible?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
So now that you know what are the faults in this algorithm, can you
Yes, sir.
can you improve this?
Sir, one thing that is general, which we see generally in fault attacks, as I had said before, the initial state, once we find, we can reverse it and find the key and the IV that were used. So one of the options could have been that the key scheduling algorithm could have used key bits to make it, that reverse would not be possible. So that could be one thing, that obtaining state bits will not lead to obtaining the key bits. That could be one thing. The second thing is maybe. So this was one thing that I said.
No,
others will have to.
I think basically you have attacked that key scheduling algorithm, not the real algorithm, right?
Yes, sir. Yes, sir.
Yeah,
yes,
yeah.
sir.
So I think okay, fine.
Yes. So for that is.
So is there any other question from the audience? Is there any question? Okay, so over to you, Professor Sandanu.
Yeah, so how many false are required, Ruby? Maybe I missed.
For this, sir, we required 4. Minimum was 4.
Oh, only
Yes,
4.
sir.
Okay, very good. Okay, I don't have any
Thank you.
other questions. So any otherwise we can thank Ruby.
Thank you, sir.
Okay, then we can move to the next speaker.
Hi, hello, can you hear me?
Yeah.
Yes, I will try to see I can share my screen. I moved to the web browser, so yes. Do you see my presentation?
Yeah.
It works?
Very good. Okay, so let me then introduce you. So our next speaker is Andy Rusen, and title of the paper is Differential Fault Attack on Montgomery Ladder and in the presence of scalar randomization. Andy, please proceed.
Okay, hello everyone. So my name is Andy. I just finished my PhD at the University of Rennes in France and the French company Orange. And I will present my paper Differential Fault Attack on Montgomery Ladder in the presence of scalar randomization. So first, a little bit of an introduction on elliptic curves and differential fault attack. An elliptic curve is defined with a Weierstrass equation and would look like this figure on the overall prime field. And starting from a base point P and using the group operation on elliptic curves, so point addition, we can compute the scalar multiplication by an integer k. So by a sequence of point addition, we can compute k times p equals q efficiently. And what happens is that if an attacker is able to make a fault in the middle of the execution, eventually we'll get an erroneous output q prime. And the idea of differential fault attack is to exploit the difference that was made on the erroneous output q prime compared to the point q. For example, if we make the difference, which could be only depends on a few bits of the secret scalar k. And one context in which this is very useful is the signature scheme ECDSA, because signature generation always involves a secret scalar k, which is called a nonce. And one key feature of this signature algorithm is that the verification mechanism of ECDSA allows us to recover both the correct point Q and the erroneous point Q prime from the faulty signature. So it is very useful for a differential fault attack. And then if we are able to apply the attack and recover a small part of the secret nonce K, then it is vulnerable to lattice attack. So I won't expand onto this part of the lattice attack. It is explained in the paper and in many other papers. But what we just need to know is that once we have removed the part that we know on the scalar k, then if the remaining part is small enough, then we can translate all of the signatures that are collected into a shortest vector problem, which can be solved with lattice. Okay, so the first part, I will present a new proposition of a differential fault attack on a specific scalar multiplication algorithm, Montgomery ladder. So this algorithm takes as input the OR scalar k and a base point p, and it works like this. So there is a point R0 and a point R1. The point R0 is initialized with the point p, and R1 has 2 times p, so the point p added with itself. And on each step of the algorithm, there is always a point addition and a point doubling. So when the scalar bit is 0, the result of the point addition is stored in the point R1, and the point doubling is made on the point R0. And when instead the scalar bit to be processed is 1, then the result of the point addition is stored on the point R0, and the result and the point doubling is made on the point R1, and so on until the end of the scalar multiplication. And then the point that is in R0 at the end is the output that we are looking for, k times p. To summarize how the algorithm works, we need to really retain as information those two things. There is a loop invariant, and if we look closely at each step, the difference between the point R0 and the point R1 is always the point P. And using this, we can rewrite what happens at each step. In fact, what happens is that the point R0 is replaced by 2 times R0 plus the new bit times the value of the invariant. And this is what happens if, of course, everything occurs correctly. And using that, it becomes easier to explain what happens if an attacker disrupts this execution. The idea of a fault attack is to suppose that an attacker is able to invert the point R0 and R1 somewhere in the middle of the execution of the algorithm. So what happens is that the difference of the point R0 and R1 will not be the point P anymore, but the point minus P. So starting from this moment on the execution, the scalar multiplication will use this new invariant. So when we are going to process the next bit, the point R0 is multiplied by 2, then we add the new bit times the new invariant, and so on with the next bit, until all the least significant bits are processed. So now it is easy to, with this description, to see the expression of the point Q prime. So I have represented with K, we had the most significant bits that were processed before the fault, and K with a bar for the least significant bits that were processed after the fault. So now what happens is that if we make the difference of the point Q and Q prime, we see that the most significant bits are cancelled. So we get a point that only depends on the least significant bits. And alternatively, we can make the sum, which will depend on the most significant bits. So it depends for whichever case it's appropriate. So if the fault occurs near the end of the scalar multiplication, then we compute the difference, and we are looking for the least significant bits, maybe by an exhaustive search, or maybe by running a discrete logarithm to search the value in a smaller range. And there are a few details interesting for this attack, in that we have seen that the fault only inverts the point R0 and R1. So it does not impact the point additions in the scalar multiplication. So those operations are still valid elliptic curve operations. So the point R0 and R1 will still satisfy the curve equation. However, since we have a change, since the invariant has changed from P to minus P, then if we check the consistency of this value, we can detect the fault. Well, that's true except for specific formulas. Let's take a look at the X-only formulas. Those formulas only use the X coordinate of the point R0 and R1 in the point addition formulas. So we cannot distinguish the point R0 from the point minus R0 because those points have the same X coordinate. So the difference R0 minus R1 and R1 minus R0 cannot be distinguished from each other. Basically, the point P cannot be distinguished from the point minus P. And that is true even if we try to reconstruct the missing coordinate Y, because it will yield the correct invariant. To explain a little bit about this part is because that the recovery formula will use the point P, the input, which is the expected invariant. But the current invariant is minus P, so it will introduce a minus sign, which will autocorrect itself with the minus sign of the new invariant. So basically, which will construct P as minus P. And this properties is also true for the coset formulas. So those formulas uses projective Jacobian coordinates such that the point R0 and R1 share the same Z coordinate, and this coordinate is not used in the computation. So those are pretty efficient. And when they use a recovery for the Z coordinate at the end because it is needed to get the affine output, then we have the same thing that will happen. It could yield the correct invariant. To finish this first part, I still need to address the issue of the realization of this fault. In practice, there is a conditional swap to avoid bound condition in cryptographic libraries, because it is important that the cryptographic code does not have branch conditions. It uses a Boolean variable, which is called pbit, which stands for previous bit, and keeps track of the current state of the point R0 and R1. What happens is that the point R0 and R1 will be swapped so that the point additions and the point doubling occurs with the correct values. So when pbit is 0, it just means that the points are in the normal set, and pbit is 1, it just means they are inverted. And we can rewrite the formula for invariance, such as the formula that you can see. So the idea is that under the skip instruction fault model, if we skip the instruction that update the Boolean variable pbit with the new bit of the scalar, then since it's XOR operation and the new bit of the scalar is 1, it just means that the Boolean variable will not be updated. And this will have an impact on the current state of the point R0 and R1. It just means that it will not be consistent anymore. So basically, if we compute the difference, we try to compute the formula for invariant, it will be minus p, and which is exactly the desired effect for our attack. There are some other possibilities, for example, by targeting the line 8, which will store the current bit of the scalar to be used for the next step of the algorithm. So it will produce the same effect, but starting from the next iteration. And there are also other possibilities that we're using other fault models. Some can target directly the conditional swap, but it depends on the method that is used for this conditional swap. There is one example that is given in the paper where a random fault in a register, in the register pbit, which can produce exactly the effect that the desired effect. So now the second part, I will talk about differential fault attack in the context of a scalar randomization. So it is for differential attack in general, but we can suppose that the differential fault attack is exactly the attack that I just presented. I will expand on the case of the Euclidean splitting. So the scalar is randomized with an Euclidean division using a random integer m. So then scalar k is split in 3 parts with the quotient, the random divisor, and the remainder, and everything is put back together in the end with the final point addition. So there are 3 individual scalar multiplication. And it's still possible to recover some very useful information for a lattice attack, eventually when the scalar k is a private key. The idea is to attack the scalar multiplication with the random divisor. So suppose it is our attack as I just presented earlier. So if we make the difference between q and q prime, we'll get a point that depends on the least significant bits of the value m. But this time, it's not the point p that we have at the end, it's the point r, which depends on the quotient, which is unknown to the attacker, and might be quite big, so it's not possible to recover it. Well, it's still possible to do something. There is some strategy that we can devise to recover both the random divisor m and the remainder b. First is to guess the difference that was made on the scalar multiplication with the random integer m. So basically, we can, in our attack, use the least significant bits of m. When we have done that, we can compute a candidate for the point r. And then we can apply the baby step giant step strategy. So this algorithm, it is composed of 2 parts. The first one where you compute all the possible values for b times p, which can be pre-computed because the point p is the base point. And on another side, we can compute the list of possible values for q minus m times r. So in our attack, since we already have the least significant bits of m, then we can just make an exhaustive search on the most significant bits of m. And when there is a collision, then it will produce a candidate for m and b. So overall, the cost depends on the size of the randomizer because we will need to run an exhaustive search on this value. So let's suppose that lambda is 32 bits, then it's something that can be still tractable to realize the attack. So it is very useful for lattice attack with for lattice attacks in ECDSA, because then the only part that is unknown is the quotient. And we can still use, in the case of K is a fixed private key, then we can use the Chinese remainder theorem by attacking over scalar multiplication. I'm not sure I will have too much time to address the over randomization method, but it is explained in the paper. So we can still attack the blinding with the group order, which is a classical countermeasures, which is the second countermeasure by Coron. So the scalar randomized by K plus a multiple of the base point order. It's possible if to apply. It's possible to use a differential fault attack as long as the number of bits that is revealed by the differential fault attack is larger than the randomizer. And there are also multiplicity splitting, which is a little bit complicated, a little bit more complicated. But in both cases, the cost depends on half the size of the random divisor. Yes, the randomizer. More detail in the paper about that. So just let's conclude. So I presented a new differential fault attack on the Montgomery ladder algorithm for scalar multiplication on elliptic curves, which can bypass some classic countermeasures. Well, not still possible to apply some countermeasures. I addressed that in the paper, but some classic ones such as point validation and invariant consistency check can be bypassed under some circumstances. And I presented also evidence that some scalar minimization method can still be vulnerable to differential fault attack. And finally, there are some simulations that are available on the GitHub repository, just to which address which present well, you can still take a look at it. Thank you very much.
Yeah, thank you, Andy. Any?
So is there any question from the audience? Is there any question? So no question. So over to you, Professor Santanu.
Maybe we can move to next speaker. I think some network issue.
Hello. I'll just share my screen. That doesn't seem to work. Or can you see it?
Yeah, I can see you.
Perfect.
Yeah. So let me introduce you formally.
If you can just stop screen share, please, for 2 minutes till the introduction. Thank you.
Yeah. So our last talk on this session is by Julius Hermelink, and author of the papers are Julius Hermelink, Peter Pessel, and Thomas Poppelman. Title of the paper is Fault-Enabled Chosen Ciphertext Attacks on Kyber. Julius, please proceed.
Thank you for the introduction. And yes, as mentioned before, the title is Fault-Enabled Chosen Ciphertext Attacks on Kyber. And this is joint work with Peter Pessel and Thomas Pöppelmann. As the title suggests, we present an attack on Kyber using the combination of a chosen ciphertext attack and a single bit fault attack. Kyber is a CCA2 secure post-quantum key exchange mechanism that is a finalist in a NIST standardization process and is based on the hardness of the MLWE problem. It defines 3 parameter sets. And what will be important here is that it's built from a public key encryption scheme using a variant of the FO transform. We'll be working over FQX mod x to the n minus 1. So as I said, it's built from a public key encryption that defines encrypt and decrypt function, and then the decapsylation of the key exchange mechanism works as follows. An incoming ciphertext C is decrypted to obtain the message M that was encrypted in C. And this message M is then re-encrypted using the same randomness that was originally used to encrypt it. The resulting ciphertext of the re-encryption is then compared against the submitted ciphertext, and in case that they are equal, a shared secret is outputted, otherwise the decapsulation fails. During this decryption step, the message has to be recovered from a noisy version of the message. The message here is a polynomial. I'll explain how bits are mapped to coefficients in the next slide. And onto this polynomial, there is a noise polynomial added. All coefficients of this noise polynomial are small noise. And what is important is that this noise polynomial contains secrets E and S. So either E or S give the secret key. All other terms are known to the attacker. So during encryption, 0 bits of a message were mapped to a 0 coefficient. Each bit gives a coefficient, and 1 bits were mapped to Q divided by 2. Now, during the decryption step we saw on the last slide, and that happens during the decapsulation step, this message has to be recovered from a noisy version of this polynomial. And this is done by mapping a coefficient to a 0 bit if it is closer to 0 than to Q divided by 2, and otherwise to a 1 bit. We can visualize this on a circle with the numbers from 0 to Q minus 1 mapped onto a circle. And the red points here would be the message bit with bits without any noise, message coefficients, 0 and Q divided by 2, and then noise rotates us either counterclockwise if it's negative, or clockwise if it's positive. So this gray point here would be an example of a coefficient that was originally a 0 bit and then had some negative noise added to it. And then the upper half of the circle is mapped to 0 and the lower half is mapped to 1. And of course, if the noise is small, then this gives the original bit. We can use this to construct error attacks. So if we add Q divided by 4 to one coefficient of this noisy message polynomial, then this is a quarter rotation on the circle. And this might cause an error, and this causes an error exactly when the noise is positive. Because if the noise is negative, then we rotate it counterclockwise, and then a clockwise rotation will not take us to the other half of the circle. But if we were here, for example, then this would cause a decryption error. So what happens if we add q divided by 4 and then observe decryption errors? We know if this noise polynomial containing the secrets E and S is positive or negative. That means adding q divided by 4 and then observing decryption errors gives inequalities, inviting the secret. Now, decryption errors are not necessarily, or decapsulation errors are not necessarily decryption errors. If we submit a manipulated ciphertext, then of course this will fail because of the FO transform. Otherwise, we wouldn't be CCA2 secure. A recent fault attack by Pestle and Prokop takes advantage of these decryption errors. They fault the decoder to cause the addition of q divided by 4. And then from each decapsulation that is faulted, they recover exactly one inequality, as described before. They then use the knowledge of the distributions, the secrets coefficients that are sampled from a known distribution, and update them successively using the inequalities, and this then converges if enough inequalities were retrieved. This is a powerful attack, but it has some limitations. It is prevented by shuffling the decoder. It has a very specific fault model and is therefore highly dependent on the implementation. So what we do is a bit differently. Instead of sending in a valid ciphertext, which we then fault, we first sample a valid ciphertext C and then add q divided by 4 to one coefficient. And this ciphertext C prime with this q divided by 4 error already in one coefficient is submitted to the device under attack. That means that the device never sees the valid ciphertext, but gets the manipulated ciphertext in the first place. So C prime is submitted to the device, decrypted by the device. Sorry. A message M prime is retrieved from this manipulated ciphertext and then re-encrypted by the device. While this happens, we introduce a fault, a single bit fault, that changes C prime back to C. So the device now has this re-encrypted ciphertext C prime prime, but compares against the original ciphertext C and not against the manipulated ciphertext C prime. What happens is that the device decrypts C prime, which is C with a q divided by 4 error added in one coefficient. But the result of the re-encryption here is then compared against the original ciphertext and not the manipulated ciphertext. And what we achieve by this, we have two cases. In case that the addition of q divided by 4 causes a decryption error, C prime causes a decryption error. Here, we get a different message here that is not the original M that was used to create C. And then, of course, the re-encryption also gives a different ciphertext, which differs from C. So we will see a decapsulation error here. If C prime causes no decryption error, then in decrypt, we get the same message M prime is M. And then the re-encryption also gives the same ciphertext, and C prime prime is C. So we do not see a decapsulation error. So now by observing decapsulation errors, we can actually observe decryption errors. And as we saw before, that gives inequalities. So each failed decapsulation gives an inequality, and each successful decapsulation also. So what does our fault have to do? It needs to correct either C prime or the result of the re-encryption so that this comparison works. That means it needs to be applied after decrypt was called and before the re-encryption comparison. and it needs to target either the stored ciphertext or the ciphertext obtained from re-encryption. And the fault model is to either set, reset, or flip a single bit. That it is a single bit is because of how compression and Kyber works, and that we can either set, reset, or flip is because we can control the input. We can choose if we want to set, reset, or if we don't care if we reset or set a bit. We also present a new method of solving such inequalities, those inequalities we then obtained, and we use belief propagation to do this. Using belief propagation, we improve the previous method by using less faults and requiring much less memory. This belief propagation works by, for each unknown coefficient of the secret, initializing a variable node. And each inequality gives a check node, and these check nodes then update the distributions coming from the variable nodes. So summarizing, what is our approach? Instead of sending a valid ciphertext and then applying a fault to cause the skew divided by 4, we send a manipulated ciphertext that already has this error and then use a fault to correct. Why is this better? Or why do we believe this to be better? The manipulation is performed offline. The error is already contained in the ciphertext that is submitted. Therefore, whenever we observe a successful decapsulation, that means that the fault worked. Otherwise, the decapsulation cannot work. That means if the fault is really unreliable, we can still work with it. There's absolutely no problem. We can just need more of them. The fault is also not prevented by shuffling the decoder and several other very specific countermeasures, because it may be introduced over a very long time span and at several places. And therefore, it's also less implementation specific. How many faults do we need? Here on the left side, we see the success rate and the number of inequalities. Remember, one inequality corresponds to one fault, corresponds to one decapsulation. And depending on the version, for Kyber 5.12, to be certain to be able to recover the secret key, we need 6,000 faults. For Kyber 7.6.8, we need about 7,000 faults. And for Kyber 10.24, we need about 8,500 faults. The recovery method is pretty efficient. We tested this on Intel Xeon Gold, 32 and 8 threads. And here we stay well below an hour for all our experiments. And it can actually be run on a normal laptop. There's no special hardware needed for the recovery method. Thank you for listening.
Thank you, Julius.
Is there any question from audience? Is there any question? Okay, so over to you, Professor Shantanu.
I don't have any question. Let me see in chat box. No, nothing is here. Okay. Thank you, Julius. Then let us thank him.
Thank you.
So thank you, everyone. Thank you for presenting so nicely. And thank you, Professor Shantanu and Dr. Mohit, for joining. So the next, now we'll be having a small tea break, and the next session will begin at 6:30 sharp. And we'll be there right back. Thank you.
Thank you. Bye.
Good evening, everyone, and welcome back to today's last paper presentation session, which session is focused on symmetric cryptography. And for this session, we have as session chair, Dr. Jaiprakash Kar and Dr. Debalina Ghatak with us. For question answer session, there is an announcement. For each paper presentation, after the talk of the presenter, you can keep your question in the QA chat box. And if you have more, which do not permit your time, then you can keep it in the Google Meet link at QA session. Thank you.
Good morning, good afternoon, all of you. Like the other sessions, also these sessions also have the 3 papers. The first one is proved indefensibility of enveloped XOR revisited. Second paper is sequential indefensibility of confusion diffusion networks. And the third one is that a lightweight implementation of server resistance against side channel attacks. So welcome the first papers, welcome these authors, Risiraj Bhattacharya, Mridul Nandi, and Anik Rai Chaudhary. So requesting you, one of the author, you can come to platforms and can present your paper.
So we've lost Professor Anik Rai Chaudhary. He's just reconnecting. Professor Anik Rai Chaudhary, you may begin your presentation, please. Thank you.
Thanks. So, good evening all. Welcome to this talk titled Proved Indifferentiability of Envelopes or Revisited. This is a joint work by Risiraj Bhattacharya, Mridul Nandi, and Anik Rai Chaudhary. So, as we all know, hash functions are very important building blocks of modern cryptology. We use them in various settings, and the usual security criteria of a hash function usually demands pre-image resistance, second pre-image resistance, collision resistance, etc. Now, a popular methodology for designing cryptographic protocols is the random oracle model. At first, we design an ideal system in which all parties have oracle access to a truly random function. And then we replace the random function with a good cryptographic hash function, such as MD5 or SHA-3. In this way, we can basically replace the ideal system in the real world. And Bellare and Rogaway developed this method. Morar et al. Introduced the notion of indifferentiability, which is basically a generalized version of the usual notion of indistinguishability. Suppose small f is a public primitive and we build a construction C using small f as a building block. And then we claim that it has same security as a public primitive capital F. To show this, we basically construct an algorithm capital S, which we call the simulator, which has access to capital F and which tries to mimic F. Now, if any distinguisher having access to small f can distinguish between C and small f and capital F and capital S, then basically we say that capital C and capital F are indifferentiable, and in that case C can replace capital F in arbitrary constructions. So this is the indifferentiability game in picture, and this is the formal definition. I will not be going into this. Now, whether we talk about indifferentiability or indistinguishability, one common trait is that none of them, this is assumed that the building blocks or the primitives they themselves are corrupted. To address those issues, Long and Young started the study of cryptography. Informally, cryptography represents the threat of a malicious attacker who, through some backdoor, can implement a defective primitive. Now, basically, what happens is when we implement a hash function, we either get it from some online library or we buy some software. But what is the guarantee that the software we have bought or the code we have gotten from the online library are the actual hash function and they themselves are not corrupted. Now, of course, if the defective hash function differs from the original hash function in very large amount of inputs, it will be easy to catch by randomly checking. So a common way to model the adversaries in these cases are the so-called curious but proud model. The subverted function differs from the original function only in a small fraction of the points. Now, there have been many studies to address cryptography and related issues. Russell et al. In their Crypto 2018 paper titled Correcting Subverted Random Oracles initiated the study of crooked indifferentiability. Their goal was to use the subverted hash function even in a compromised setting. Now we will first describe how the crooked implementer or the adversary in the crooked setting works. So basically what happens is that adversary in this case has at first advice string to itself. Basically, even before of any phase, the online phase begins, it queries the family of random functions on some fixed number of points and get their input-output pairs, and it uses them as an advice string. Now, after when the online phase begins, when function FL and the input X is given, it decides whether to crook or subvert FL at the point X in the following way. So it has X and FL. So then basically what it does is that it queries FLX at some point I. Basically it queries FI at some point Y, and then depending on the, of course, depending on the input X and its output Z, it queries FI at some point I and gets, sorry, FI at some point Z and gets the output W. Then depending on the pairs Y, X, L and IWZ, it decides its next query, and it goes on like this for a fixed number of times, say Q tilde. So basically after that it has a Q tilde many input output pairs to it, and depending on those Q tilde many input output pairs, it decides whether to crook FL at the point X or not. Now if we want that the subverted function family F tilde L is undetectable by random checking, we will need that for each L, probability FLX not equal to F tilde LX is very small. This is the crooked indifferentiability notion. It varies from the usual indifferentiability notion in the following way, that in this case, there is a public random string R, which is used to initialize the construction. And in the second phase of the random, the random initial value R will be sampled and given to the construction C and also to the adversary. And in the ideal case, the simulator will get the transcript of the first phase, basically that we talked about, the advice string. It will have access to that. It will have access, black box access to the subverted random oracles and the initial value capital R. So Russell et al. In their paper proved a composition theorem similar to the composition theorem proved by Maurer et al. In their famous paper. They basically say that if C and F are crooked indifferentiable, then we can replace capital F from any construction by C. This is the envelope. So this is the envelopes, and they introduce the envelope Zord construction. Informally, the envelope Zord construction can be described in the following way. Its domain is the integer set 0 to L and its cross product with the bit strings of length n, binary bit strings of length n. And if capital H is all the functions from the domain to 0, 1 to the power n, for every x belonging to 0, 1 to the power n and an initial value capital R, we define grx as the Zor of f1 x plus r1, f2 x plus r2 up to fl x plus rl, and then we apply f0 on it to get our final output. Now, while going through the proof, we discovered some inconsistency there on their proof. They basically proved a very interesting rejection resampling lemma and used that to prove their claim. Now, there were some inconsistencies. Some of them we have listed below. One incompleteness of their proof was that they basically did the proof for a single query. They didn't address the case when the adversary can find two messages M1 and F2 whose capital F values are same. Basically, capital F of M1 equal to capital F of M2. Another inconsistency for handling multiple queries comes in the following way. Basically, they call a function H and a public random string RH unpredictable if for all message M there exists an I such that Mi plus R is not crooked for H and Mi plus R has not been queried by any crooked point of H. So they then basically argue that if the desampling is done on such an index I, the transcript of the interaction will not change. But this claim is justified for a single message and not for multiple queries. We can basically make batch queries of the type of M and M plus all one strings. And in that case, the adversary can always query M plus one for, basically if the adversary is the subverting algorithm can always query M plus one for M. And in that case, while answering the queries for G of M plus 1, those values will already be previously fixed and that case has not been addressed. Okay. And the main technical claim of that paper was that if we take the probability over the resampled F function, then G tilde Rx, basically the subverted GRX value, this belongs to some set is very small because G tilde Rx is uniformly distributed under resampling distribution. Now in their case, they took E to be the crooked set, but the crooked set of F0. But the problem is the crooked set of F0 can depend on other functions F1 up to FL because if the subverting algorithm at F0 can query F1 up to FL. So those two, the event E and the G tilde Rx, they are not independent. So we cannot upper bound in that way. So after going through the proof, we tried to correct their proof and we have succeeded in that. We mentioned here that we have communicated the issues with the authors and they have acknowledged them. And since then, they have uploaded a revised version in ePrint. Their new version uses techniques like discrete Fourier transformation, while our proof depends on simpler techniques. Okay. So we will present a brief outline of the proof. We use the game playing technique. So there are 4 bad events. The 4 bad events can be described as following. That first bad event is that the input to F0 belongs to the crooked set of F0. That is the obvious bad event. The second bad event is the input to F0 already belongs to the previous input-output pairs or the previous transcript of the input-output pairs. The third bad event is that the input of F0 at some ith query collides with some query at the jth stage. Basically, for some j less than a, basically the input has already occurred in the transcript before. And the fourth bad event is that the input of F0 belongs to query set for some x such that x belongs to the crooked set of F and x has already appeared in the transcript. So we bound the individual bad events and then add them to get our result. Informally, we are able to show an security advantage of the order of q tilde q2 square by 2 to the power n plus L q tilde q2 epsilon to the power 1 by 16, where q tilde is the maximum number of queries by the subverting algorithm per query, and q2 are the number of queries to the 2 oracles, and L is the length, basically the 0 to L, that function family from where we sample basically the length of the indexing set. Okay. So basically, we define something called a good point function pair. Informally, a pair YF is good if Y is not a cooked point for F, as well as Y is not queried by a large number of X. And then with appropriate parameters, we are able to show that when we take the probability over Y and F, that the probability YF is not good is very small. It is of the order of epsilon to the power 1/4. Okay. We basically then construct a set of which we call critical values. They consist of pairs, the random string of the public random string R and random functions F, such that for each M there exists an index I, that M plus Ri and F. M plus Ri is good for Fi. That is basically M plus Ri is not a cooked point for Fi, and also M plus Ri has not been queried by any cooked point for F. And we call such a G the critical set. We are able to show that when we take the probability over RF randomly, that for basically R and F both are sampled randomly, they doesn't belong to critical set. That probability is very small. It is of the order of epsilon 1 to the power 1/8 into 2 to the power minus n. So TR subscript J denotes the transcript after J queries. And we call that the transcript after I-1 queries is good if the probability that RF is good, given that F agrees up to the with the transcript up to I-1 at query, is close to 1. And if we fix K, we say that F is called good, TRI good, basically good with respect to the transcript up to ith query. If agrees with the transcript up to I-1 at query, and alpha K F, basically M plus RK comma F is good. Then for any TRI good F, we show the existence of a set which has set S which has size almost 2 to the power n, that is almost the size of the whole domain. And for all beta, if beta is the function that we basically that agrees with F on all points but alpha, where we set F of alpha equal to beta. So for all such F beta, so if is TRI good if there exists a size set S of size almost size 2 to the power n, such that for all beta belongs to it, all beta belongs to S, if beta is also TRI good. So then if we take any event E, we have, when we condition the probability of E given TRI minus 1, we are able to show this lemma that it is less than equal to the summation from K equal to 1 to L, that probability is taken over F here. Probability E given alpha K comma F is TRI minus 1 good, plus some 3Q tilde epsilon 1 to the power 1/16. So then we replace our bad events, bad 1AI, bad 2AI up to bad 2CI with E. And using this lemma, we can get the individual bad events. And after that, we sum them up to get our result. So these are the references. Okay, I have, this is all. So if you have any questions.
Thank you, Dr. Anik. Okay, thank you, Dr. Anik, for this wonderful talk. So any questions from the audience? So I think there is no question from the audience.
I have one question. The link for the Google Meet is the same as you have sent in the Gmail, right? Previous day. For the Q&A session.
I have just shared it on the personal chat for you on the Zoom platform over here. I have sent it to you separately.
Okay, thanks.
Okay, then thank you, Dr. Anik, for your time, and thank you, the audience, for your attention. Thank you very much.
Okay, the second paper is sequential indefensibility of confusion diffusion networks, and the authors are Kui Da, Sanjeev Hu, and Chun Gu. So requesting one of the authors, you come to the platform and can present your paper.
Oh, okay, thanks. Hello, everyone. My name is Chida from Chandon University. Our topic is the sequential indefensibility of confusion diffusion networks. First, let us introduce the definition of substitution permutation network. We call it SPN for short. Concretely, SPN yields an WN-bit block cipher by interrenting the following three steps. The first is key addition by XOR a round key with WN-bit state. Second is substitution. It breaks down the WN-bit state into disjoint chunk of n-bit and evaluate a small bit permutation, typically called an S-box on each trunk. The last one is permutation. It applies a big size permutation with simple construction. SPN fits into the confusion diffusion paradigm. The permutation can be viewed as confusion, while the permutation is viewed as diffusion. The idea go back to the festival and even back to Shannon. Various popular primitives have been built upon this, such as the block cipher, like AES and rectangle, and also the hash functions such as the permutation of the SHA. We consider the S-box are independent random permutation, while the D-boxes are fixed explicit nonlinear permutations. Previous work introduced the new model called confusion diffusion network in 2016. It is similar to the SPN, but do not have keys. We can view CDN can be a domain extension maximum for permutations. But here is the question: how many rounds is enough? And next, we introduce the definition called indefensibility. How do we prove CDN can be seen as a permutations? So we use the definition called indefensibility. In this setting, distinguisher D is trying to distinguish between the real world and the ideal world, which means the distinguisher is trying to distinguish the CDN construction from a random permutation. In the real world, distinguisher has Oracle access to the construction CDN, and it also has Oracle access to each individual S-box used in our construction. In the ideal world, the CDN construction is replaced by a real giant random permutation, and to have the same interface in the real world, we need to use a simulator. The simulator has Oracle access to the random permutation, and it has to make up answers to look consistent with the permutation. If we consider the distinguisher is sequential, called sequential indefensibility, we restrict the distinguish order to be primitive constructions sequential. In the first phase, the distinguish query the underlying primitive S-box and the simulator. The number on the arrows represent the order. However, if in the second phase, it queries the construction CDN or the random permutation. In this situation, the distinguisher could not just query this part. However, if we change the order of query, the situation will be different. If the distinguisher first query the construction, then the distinguisher could not query another primitive security model anymore. It could just query this part. Because we restrict the query order of distinguisher, it is weaker than the full indefinability. The sequential indefinability notion has the advantage of being the simpler and easier to use in the proof, but it is still strong to imply the correlation intractability. Though this introduce the model of CDN and establish the probe security in the plan indefinability framework using the nonlinear debox. 5 rounds are proved indefinable. In our work, we first exhibit an attack against the 2-round CDN, which shows the tightness of our positive result on 3 rounds. We prove that the 3-round CDN with nonlinear diffusion layer achieve the notion of sequential indefinability, which is our main result. First, our 2-round CDN constructor is shown in the figure. We need 3 steps as follows. First, we choose n-bit string B, D1, D2 such that the first n-bit output of debox are identical. Second, we query A1, A2 to obtain the A, C1, and C2. Third, we obtain the F1, H1, and F2, H2 by querying the oracle P. If P is a 2-round CDN oracle, it is necessary that hold that F1 is equal to F2, which means the distinguisher always put output 1. On the other hand, if P is a random permutation, the probability that distinguisher output 1 is just Q squared divided by 1 by 2 to the power n within Q queries. So the distinguished advantage is thus 1. The attack is work. Next, we show our 3-round CDN construction with input and output is both the WN bit. Each Xbox is an n-bit permutation. We call n is the wire length and the W is the width of CDN. We use nonlinear diffusion layer in the proof of the 3-round CDN. Apparently, debox input and output size is WN bit because nonlinear debox satisfies certain combinatorial requirement and it is more security than linear debox. We will introduce 2 combinatorial properties of debox to simplify the expression. We let the input of debox is x1, x2, x3, x4, which means that W is 4. We only focus on one of the input. For any fixed x2, x3, x4, and for any y2 star is and for y2 star is another values in output. There is a low probability that exists the x1 such that y2 is equal to y2 star. Here is another property. X2 prime, X3 prime, and X4 prime is other input. For any X2, X3, X4 not equal to X2 prime, X3 prime, X4 prime, there is a low probability that exists the X1 is equal to X1 prime, such that Y2 is equal to Y2 star. There is an important sense is how to build the simulator. We use chain complete technique. It requires the simulator to detect particle computation chains formed by the query to the distinguisher and complete the chains in advance. Simulator is ready to answer the queries in the future. To simulate the answers that are consistent with the random permutation, simulator has to use the answer from a permutation to define some simulated answers. This action is called adaptation. In this situation, the work of our simulator is follows. The distinguisher first makes the query X with which is one of the input of the second layer X boxes. the simulator extend x to xb and yb, which extend the length to n to wn. We obtain the xa by yb and xa by xb. Then the simulator query the random permutation to get yc. Finally at the last layer of the Xbox, the simulator makes the adaptation by using xc and yc. If the simulator makes the query y, which is one of the output of the second layer Xbox, it is similar to the situation we talked about. We simplified the previous model. Z is the WM bit random permutation, S is the simulator, P is the small random permutation with n bit. The most important thing is we need to find out the distance between the real world and the ideal world. We need to add an intermediate system. It functions as a bridge between ideal world and the real world. Simulator has both access to Z and P, and the distinguisher can query the simulator or query the CDN construction with Oracle access to S. We first find the distance between the ideal world and the intermediate system. We can see the distinguisher first query the simulator with Oracle access to Z and P, both in ideal world and the intermediate system. If the pair is good, the answer that the distinguisher received are identical. On the other side, Z is an ideal primitive and the CDN is the real structure. So the distance between the real world and the sorry, this is wrong. This is G1 and G2. So the distance between the ideal world and the intermediate system depend on the pair ZP. Next, we find the distance between the real world and the intermediate system. We noticed that the real world only have access to P, so the situation is different. The most important thing is how to get from the pair ZP to P. So we use the random mapping to solve it. We define the map gamma on tuples of random permutation ZP. When the pair is bad, the map is a special symbol. When the pair is good, it will be the tuple of the particle permutation beta. For the tuple of the permutation P in the real world, we said P extend a tuple of particle permutation if for each beta and P agree on all entries. So we can use beta to find out the distance between the intermediate system and the real world. Thereby, we can find out the distance between the real world and the ideal world. So this will be a summary of our work comparing to the previous work. It shows that the security bound query complexity and the same complexity for our work and the previous work. Thank you for listening.
Thank you for this wonderful talk. So any questions from the audience?
Yeah, I have one question. This is Mridul. Hello, yes. Can you hear me? Hello, can you hear me?
Yeah.
Yeah, so I
can hear you,
want to know that the attack you have described, it is the classical attack or the public or the sequential attack for the 2 round?
Yeah, I can't understand.
The 2 round attacks for the CDN, is it the public? Is it the sequential adversary or the classical adversary?
It is a sequential adversary.
Okay, I probably didn't understand correctly, but okay, so then that's fine. That's what I think it should be. But anyway, okay, that's fine. Yeah, I'm done.
Okay. So if there are no more questions, then thanks to the author for this wonderful talk. Thank you so much.
Yeah, thank you.
So the last paper is this session is a lightweight implementation of Cyber resistance against side channel attacks. The authors are Abu Bakr, Kamar Mohajarni, Bhaid Bardang, Jens Peter Kaps, and Chris Gaj. Welcome, one of the authors. You can take the platform and can present your paper.
Hello, do you hear me? Do you see my screen now?
Yes.
Okay, so thank you for the introduction. So this is Abu Bakr Abdul Qadir presenting our work, a lightweight implementation of Sabre resistant against side channel attacks. This is a joint work with Kamir Mohajirani, Vid Dang, Jens Peter Kaps, and Chris Guy from George Mason University. So the development in quantum computing nowadays threatens all our public key infrastructure. So algorithms like RSA, ECC, all of these are vulnerable to attacks from quantum computers. So Sabre is one of the candidates that are believed to resist attacks from quantum and classical computers. And it's basically a key encapsulation mechanism that you can use to exchange keys from between communicating parties securely. It's a lattice-based scheme based on the hardness of modular learning with rounding, and it has been shown so far to be very efficient to mask in software. Basically, if you need to protect it against side channel analysis in software, it was shown already that that will be efficient. So now Sabre is a NIST PQC finalist competing to be the PQC standard to be used for quantum safe encryption or key encapsulation. So in this work, what we do is investigate the effect of applying side channel countermeasures on full hardware implementations. So previous works concentrated on software implementations and software hardware co-design implementations. So in this work here, we concentrate on a full hardware implementation, apply side channel resistance, and see the cost of that protection. So side channel analysis is a well-known threat to the deployment of algorithms, especially in IoT devices, where you have the adversary having access to measure power or measure also electromagnetic radiation or timing, and that will threaten successful deployment of these systems. So basically in any cryptographic system, you have your main channel. For example, you feed it and you feed your device plain text and you get out ciphertext. This is the main channel, but you also have side channels like timing, power consumption, electromagnetic radiation. And by measuring these side channels, the adversary can learn information about the sensitive information, such as the key, and break the whole encryption system. So for this reason, you need countermeasures to resist these kinds of attacks. The problem with countermeasures are that they're costly. For example, in hardware, they can increase the area, and they can also make your device performance also reduced, and that's algorithm dependent. So for each algorithm, you need to do a careful study on that algorithm to see what's the effect of adding side channel countermeasures. So we did this study on the Sabre algorithm. The countermeasure that we are interested in this work, it will be masking. And basically the idea of masking is that you have your sensitive data and then you split it into shares. You compute on those shares securely and make sure that you're doing the computation correctly and at the same time not leaking any information about the secret that you're trying to hide. One of the types of sharing is Boolean masking. Basically, you split your sensitive data into shares such that when you XOR these shares, you get the sensitive value. And there is this arithmetic sharing. When you add the shares, you get the sensitive value. So these are one of the two. These are the two most common types of masking that you can use. And also, depending on the platform itself, you need to make sure that you're applying the correct countermeasures. So, for example, in hardware, there is a phenomenon called glitches. Basically, these are temporary changes in the signal before they stabilize at the end of the clock cycle. So these glitches can also cause some leakage. And there are some countermeasures that are suitable for hardware. For example, threshold implementation and domain-oriented masking. These are types of countermeasures that are designed to resist glitches. In general, in any masking scheme, linear operations are trivially masked, but nonlinear operations need much more work. So our methodology to do our work on Sabre was to start first from a baseline lightweight design, and basically that will give us two benefits. First, in the protective design that will build on top of this will be some of the components will be used as is. So for example, polynomial arithmetic and many other functions will be used as is. So that will give us this reusability of resources. And the second is that since we are building on this baseline design, we can directly compare these two designs. So we have a meaning comparison on the cost of adding countermeasures on this design. So the design that we built uses the transfer level, register transfer level methodology, and we coded we described it using VHDL and Chisel language. This design uses a flexible polynomial multiplier based on schoolbook methodology, and it's very flexible. And also we have a very flexible SHA-3 unit. So these are the two main operations, the most resource-consuming operations in our design. So having them configurable makes the whole design very flexible. So in general, we store everything here in this memory, in this RAM, and we feed the data into the polynomial arithmetic units, and the data goes back into memory. So basically, before you feed it into the polynomial arithmetic units, you go through these width converters, which are responsible for changing the byte strings stored in the memory to coefficients that will be fed into the polynomial arithmetic units. And then you pack these polynomial coefficients into byte strings back using this width converters. You also have the 3 unit and sampling units that are also used. So here are some of the major units that we use in design. So for example, has a polynomial multiplier, and the flexibility comes from set the numbers, the number of the multiplication units that we instantiate inside of it like this, and that will give us area performance trade-off. We have also the sampler, which is responsible for getting the binomial samples, and it receives its input as uniform samples, and then it will calculate from those samples the binomial samples. We have also the width converters that I just discussed, and it's responsible for packing and unpacking polynomials from memory. So Mass Sabre was already discussed in software, studied in software, and this data flow diagram from Berendonk and others shows how you can process shares securely in Sabre. So the idea of this data flow is that you split your secret key, your private key, into 2 shares additively, such that when you add the 2 shares, you get your original private key. The private key is the most sensitive resource in Sabre because it's used long term, and it's used in the decapsylation algorithm. So the attackers will be after this key, the private key. So the idea is that you split it into shares, and then you compute on these shares securely. The main challenge here in Sabre is that some of the operations like SHA-3 favors Boolean masking, some operations favor arithmetic masking. Some of the operations, for example, that do polynomial arithmetic favors arithmetic masking. So you need to securely do this conversion between arithmetic and Boolean masking. So for our design, we chose to duplicate all the linear logic and redesigned all the nonlinear components. So this is how our mask saber design in hardware looks like. And if you notice that it looks like two copies of the unprotected data path in the right and the left, these can process one share securely, and you don't have to mix the shares. However, we have these units labeled in highlighted in red here in the middle. All of these units have nonlinear operations inside of them. So in nonlinear operations, you need to mix the shares. So in that case, you need to be very careful and mix them in such a way that you don't leak any information. So what happens here in this design is that data comes from the memories on the right and the left, go through the polynomial arithmetic units, and then through the nonlinear units where you have to mix the shares, and eventually each nonlinear unit will output two shares that we can securely merge back into the respective parts of the data. So here I'll briefly discuss some of the major units we used in the masked hardware. So for example, this is the logic shift unit. So in the compression is done by bits on the polynomial coefficients. So basically, operation is free in unprotected hardware because you just discard the bits. In the protected implementation, it's more difficult because you receive arithmetic shares, and the logic shifting is a Boolean operation. So the idea of this, which is taken from the work by Brendonk and others, we did the hardware implementation for that algorithm. The idea of it is that it receives arithmetic shares, do the shifting, and eventually output arithmetic shares that are can be usable for the polynomial arithmetic units. This is a sampler that we used in our design based on an algorithm by Schneider and others. And basically what it does is receiving uniform samples and output binomial samples, and it takes one bit at a time from each input of uniform samples, do a conversion to arithmetic sharing, and accumulate those until you get your binomial samples. This is how our SHA-3 unit looks like. And basically, this is a very configurable SHA-3 unit. It can do SHA-3 256, SHA-3 512, and Shake 128. And it has a very flexible design. It can do, we can do a performance area trade-off. And basically, that's done by configuring the number of slices that we can process every clock cycle. Domain-oriented masking was used to protect this design. So here I'll briefly discuss the results. So to assess the security of our design, we performed leakage assessment using the test vector leakage assessment methodology. And on the top, you see the graph on our protected implementation, while the random number generator is disabled, the PRNG is disabled. So once you disable the PRNG, you're basically disabling the countermeasures that you're using. And we can clearly see that there is a leakage that shows that, and this is how what we expect. And this also shows that our setup is able to distinguish leakages. The second graph on the bottom, we enable the PRNG, enabling all the countermeasures that we have, and clearly we can see the t value within the threshold, and that one spike at the far right is when we compare the ciphertext against the re-encrypted ciphertext, and that should not give the adversary any advantage. So here is a comparison of our work with previous works. There are two implementations of masked saber. One running on ARM Cortex M4, and one is accelerators on a RISC-V implementation. So this shows that our design, compared to the baseline design, we got from this number of LUTs to this number of LUTs. Basically, what happened is that it's almost 3 times the LUTs, because we duplicated the data path, and there are some units that grows in much in a non-linear fashion. The DSP units also has been doubled, and we can see that the latency is around 1.36 times. So this summarizes the cost of protection in our design. So the LUTs grows by 2.9 times, DSPs grows by 2 times, and the latency by 1.5 times. Here is a breakdown of the major units that we have in our design. And basically from this diagram, we can see that the polynomial arithmetic, the polynomial multiplier, SHA-3, and the main memory take most of the area. But when we go to the protected design, we can see the protected design below here. We can see that the sampler, the central binomial sampler, is also very significant in area. So to conclude, the cost of protection in our design was 2.9 times the LUTs, 2 times the DSP units, and 1.4 times the latency. Our protected design is also 29 times faster than previous NAS software running on ARM Cortex-M4, and 26 times faster than the software hardware co-design based on RISC-V that was reported previously in literature. We can clearly see that to improve these results, we need to concentrate on the polynomial arithmetic unit and the SHA-3 unit for both the unprotected and protected designs. But also in the protected design, the CBD sampler is also significant. So reducing the size of that and improving its performance will be useful. So for future work, we suggest focusing on fault attacks and deep learning based attacks, and also further reduction in resource utilization and performance improvements can be achieved. Thank you for listening.
Thank you very much for this wonderful talk. So any questions from the audience? And so can I ask one question? Yeah.
Sure.
So you have used SHA-3 in your design, and you mentioned that similar kind of designs can be made with SHA-256 or 512. So have you tried, I mean, is there any drawback in those SHA functions? That was my question.
No. Yeah, so in Saber, what we do is inside the algorithm, it needs to use SHA-3, 256, 512, and Shake 128. So all of these sub-functions of SHA are used in Saber. So our design is flexible. So it's a SHA-3 unit, but it can do all of the 3 functions, and all of them are actually needed in Saber.
So any SHA function can be used for the same design?
We need SHA-3, but specifically SHA-3, 256, 512, and Shake 128. So all of these functions will be called, all of those will be needed. So you cannot use one and discard the others. The algorithm will call each of these individually.
Okay, thank you so much. So
Thanks.
any more questions from of somebody online?
So there is no any questions in this chat box also. So anyone in this physically in the venue who might be any questions, they can ask. Here there is no any questions in the chat box.
So I think there is no question from the audience here. So let us thank the author again. Thank you.
So thank you all. Thank you to the authors who have presented their paper so nicely. And thanks to the session chair, Dr. Kaur and Dr. Ghatak, for being there. So now we'll be having a 15 minutes break, and then the Indocrypt 2021 drum session will be beginning at 7:45 p.m. sharp.
Thank you.
vuvuzelas, or like you can have some electronic guitars, or you can basically have some ninja technique as well. So to stop the people if they run out of time. And there is a new concept called buying time. So that was introduced by Costello et al. In Asia at Asiacrypt 2018. So there, apart from the limited time, the challenge was if you can drink this beer bottle bottoms up in one go, then you get some extra time. So for our case, for stopping people here, I'll use this basically. I'll use this whistle to stop people, and for online people, I have a better option. So just you can mute them. And for buying time, what we have, so I have this water bottle because no question of beer. So I can. So if you want to buy time, you may use this. Okay, so now let's go to the main part. So here is basically the speaker. So we'll start with Orgo Bhattacharya, then Debolina Ghatak, Julian Leitke, and then Pedram Hosseini, followed by Muhammad Usama Sardar, Jyotirmoy Pramanik, Chandon Goswami, and Surendra Talwari. So we'll start with two offline speakers, and we'll start with Orgo Bhattacharya. So Orgo. এটা চেঞ্জ করতে হবে নিউ শেয়ার okay. So one more thing, so each speaker will get exactly 6 minutes for their talk. Fine. So after 6 minutes I'll blow this whistle.
Hello. So, good evening, everyone. I will try to storm through this PPT. This is about a recent paper which I was a part of. These three co-authors, as mentioned on board, and this is currently under review, so not published yet. So I will first give a brief motivation behind this work. So in Crypto 19, Chen et al. Proposed three variants of some of Mansur ciphers. So in these two cases, as you can see, they used, in one case they used one single permutation and two independently sampled keys, and in the other case they used two different permutation and used the same secret key, and they proved in both the cases that the security they obtained is the birthday bound security, that is n by 2 bit security. And in the third variant, they used two different permutations and two independently sampled secret keys, which helped them obtain beyond birthday bound security, that is 2n by 3 bit security to be precise, and they also proved that to be tight. But as you can see in this construction, it's fixed length PRF, that is the input is n bit and the output is n bit also. So in this context, we tried to address the question that we tried to convert it to a variable length output PRF actually. So by right click on. Yeah, sorry. So we tried to address this question in our work, that how to stretch the output side, because in their construction it was the constant output length PRF. So yeah, so this was our not the exact construction. This was the building block of our construction. It's the algorithm for generating random key stream. We named it as ZOR PP star. As you can see in this case, we actually the idea was like this, that the messages were coming in terms of blocks. We divided the message blocks in some chunks. For example, in this particular case, the length of the chunk was two message blocks. So as you can see in the left half there is a processing, and in the right half there is another processing. These each half is processing one single chunk of messages, and the first line of the left half is being XORed with the second line of the left half to give a beyond bound secure output, which is the first key stream, which will XOR with the first message block to give the first ciphertext block, and it will go on processing the messages like that. And one thing to observe is that in each chunk, the permutations we have used, they are different permutations, because we are following the third variant of Chain et al. Proposal, that the permutations are different and the keys used are independently sampled. So and this is the construction where we are actually XORing the message blocks to get the ciphertext out, and using the nonce in the input of the construction, and the nonces are padded, and the padding is used as unique padding for each message chunk processing. But as we are following the third variant, where we saw that a single input is giving beyond bound secure output if we are using defined permutation and independent keys. So in this case also, the key stream will once we XOR the key stream with the message, then we get the beyond bound secure ciphertext blocks. This is the key scheduling matrix which we used, and in our particular case, we instantiated the variables with these values, and in that case, we named our construction as CNCPP only. We obtained, as expected, beyond bound security with a factor of 1 by W squared. W is the length of each block, so it's a constant factor. So this was an intuitive question that if we can reduce the number of master keys to 1, we analyzed this case and we got a negative answer to this question actually, that if we use a single secret master key, then we can't go beyond bound security, and we will be restricted to n by 2 bit security only. More precisely, the key scheduling matrix, which we can see here, it must have one necessary criteria, that each of its columns should be linearly independent. That is, it should be full rank if we have to go beyond bound security. And another question which we tried to address is that if we can reduce the number of permutation to 1. So in each block, in each chunk of blocks, we, for example, the length is W, then we had W plus 1 permutation calls, and all those W plus 1 permutations calls were made to different permutations. So we tried to minimize that number, and we got a positive answer here, that if we domain separate one single permutation, then one single permutation of a little bit bigger size should suffice. So this was the one single message chunk processing in the previous from the previous picture, where we can see that in the previous case we used P0, P1, and P2, 3 different permutations. In this case, we just domain separated them by 3 different bits. In this particular case, we have to use 2 bits because 0, 1, and 2. So, and we will get again 2 power 2 n by 3 bit security with a factor of 1 by W to the power 4. Thank you. Any question?
Okay, so our next speaker is Dr. Devalina Ghatak from TCG Crest, Kolkata. Over to you, Devalina.
Okay, thank you, Dr. Datta. So the topic that I am going to talk about today, it is a bit different from pure cryptography, but it is something related to security. So it is, I will discuss some recent techniques that have been developed for synthetic data generation, rather secure synthetic data generation, and I will discuss what that is in my talk. And then I will just briefly say about an intuitive idea about what work we are thinking of doing, but it is an unpublished work, incomplete work till now. So I will just discuss about mainly about the problem that we are thinking about. Okay. So I'm mainly concentrating on statistical data sets. So what is a statistical data set? It is mainly we are talking about microdata, where there are some n individuals and some m attributes corresponding to each individual. And due to release of statistical data sets, some privacy issues may arise. So what that is, to understand that, I have given an example. So this data set was taken from Kaggle. So they have released this insecure data set here. So you can see that this is an original data set which is available in Kaggle. So these are some information related to some individuals, their age, gender, then BMI. This is a medical data set basically. And then the charges that each individual have paid for their treatment, that is also mentioned here. So now this is available in the market, this kind of data set. Now, suppose some intruder who is trying to guess something, or from this data set, somebody is trying to see that what charges have a particular individual paid. Okay, so that might hurt the person sentiment in some way or the other. So, or somebody may also get hurt by the attributes like smoker, whether they are or not. Okay, so here I will talk about the kind of attack that we are thinking about here. So at first now, a person, an intruder may have an idea about the individual he is targeting about. He may know that that person is a male senior citizen and he has 3 children. These are very common things that a person usually knows about an individual. And he also lives in the Southeast region, right? So these kind of informations are usually well known to everyone. These are public informations. Now, if some intruder has this kind of information about his target one, so now only from those public informations, you can see clearly that there is only only one row here, and it was in the whole data set. It consisted of about 3,000 or more than that individuals, and there was only one row who was a senior citizen, and he lived in the Southeast region, and he was male, and he has 3 children. So these informations were corresponding to only one person. So from that information, the charges paid by them are one can find out. Also, they can find out whether they are smoker or not. These kind of informations get leaked. So whenever there is some raw data set getting released in the public, these kind of security questions may arise. Okay. Now, what is desirable and what is not desirable in this situation? So for a statistician or for an industrial person who is trying to find out some statistical information from the released data, what they're trying to say, what is desirable to them is the statistical information, right? So the desirable questions may sound like this, that how many people have income ranging between this or less than 60,000, 50,000 or something like that. But for one person, if the information is not available, then that is not a problem for the statistician. So one may ignore these individual informations and only keep the statistical informations while releasing something from a data set. So whenever an information is getting released from a data set, we may ask the question whether it is secure or not. So in the last, this problem has been dealt for more than 15 years now. So the concepts that have been developed for the privacy guarantees are like there are these privacy guarantees like differential privacy or its variants. So they ensure a privacy guarantee to any statistical information released from a data set. Okay, so till now people have seen many differentially private means, medians, and some common statistical functions like that, or even quantiles. So people have come across that. Now, one very challenging problem in here is the generation of a synthetic data. So is the generation of synthetic data set. So what is a synthetic data set? A synthetic data set is a false representation of the true data set. So okay, I think the time is over. So I may skip. Okay, these are some well-known techniques, and this was intuitive idea. So I didn't get time to discuss.
Okay, thank you, Devalina. So round of applause for her. Okay, so the next talk would be by Julian, and Julian from University of Stuttgart, Germany. So over to you, Julian.
Can you see my slides now?
Yeah, absolutely fine.
Oh, perfect. Hello, my name is Julian Dietke, and I present you Ordinos, which was published at EuroSNP 2020. It is joint work with Ralf Küsters, Johannes Müller, Daniel Rausch, and Andreas Vogt. So Ordinos is the first provable, secure, verifiable, tally-hiding remote e-voting system. So let us briefly discuss what these properties are. So verifiability means that parties are able to check whether the claimed result of the election is correct. This check can be performed by individual voters, but it is not restricted to participants of the voting protocol. Thus, everyone can verify the election result. The next property I want to talk about is tally hiding. In order to explain what tally hiding is, let me first give you an intuition on how traditional e-voting systems and paper-based elections work. So I will roughly go over a typical voting flow. So we have a set of voters who cast their ballots and send them to the bulletin board. Then the votes are counted and a full tally is published. Now we can compute the result of the election based on the full tally. But often the voting result consists of a single winner or a ranking of candidates. Thus, this voting flow reveals more information than necessary. In particular, we are only interested in the election result, not in the full tally, which is nevertheless also published. Revealing the full tally has several downsides. So, for example, in some elections, like within companies, student associations, or in boardroom elections, it might be embarrassing for the losing candidates to publish the possibly low number of votes they received. Additionally, publishing the full tally lowers the privacy of the voters. For example, for elections that are carried out among a small set of voters, like in boardroom or jury votings, revealing the full tally leads to a low level of privacy, because the vote of a single voter is only hidden behind a low number of other votes. Therefore, even if you only want to know who won the election, a voter might not vote for her actual preference, knowing that nevertheless the full tally is revealed, and hence her vote does not really remain private. Moreover, some elections have several rounds. In particular, they might involve runoff elections. In order to get unbiased voters' opinions, one might not want to reveal the tally of intermediate elections, except for the information which candidate move on to the next round. So these examples illustrate that for some situations, it is desirable to not publish the full tally as part of the tallying procedure, but to only publish the actual election result. This concept is called tally hiding, and it works as follows. So in tally hiding e-voting, we only reveal the election result in which we are interested. In particular, the full tally is not revealed. The concept of tally hiding has many use cases. For example, as mentioned before, it can protect the privacy of the voters and candidates. There are some associations that use tally hiding for exact this reason. But what about verifiability? How can we verify the election result is correct if we do not see the full tally? Can we verify the result and hence trust the result? And the answer for this is yes, we can. So on the one hand, we have verifiability, and on the other hand, we have tally hiding, where we only want to reveal the election result. With Ordinals, we combine both of these properties. Ordinals is the first provable, secure, verifiable, and tally hiding e-voting system. At its core, Ordinals combines homomorphic encryption, zero-knowledge proofs, and MPC protocols to achieve the desired properties. With that being said, Ordinals opens new possibilities for votings because it allows for elections that cannot be done with traditional e-voting schemes or traditional paper-based voting. So thanks for your attention, and if you want to learn more about Ordinals, you can find information in our technical report linked here on the slides.
Okay, can I continue?
Professor Datta, we can't hear your audio.
Hello, can you hear me now?
Yes.
Hello. Okay.
Yes.
Okay, so thank you, Julian, for your talk, and welcome, Pedram. So, Pedram, you can continue.
All right. Yeah, thank you very much. So, welcome to this short talk on DY star, a modular symbolic verification framework for cryptographic protocols. This is joint work with Karthik Bhagavan, Abhishek Bishawat, Quico Do, Ralf Küsters, Guido Schmitz, and Tim Würtele. And this work is published at EuroSNP and at CCS this year. You can find all papers and code at our project website, reprosec.org. So when looking at mechanized symbolic protocol analysis, there are basically two big lines of work. On the one hand, there are specialized $Viao style analysis tools, such as Tamarin and Poveriv. And on the other hand, we have tools based on dependent type systems, for example, RCF and F7. Now, often these dependent type systems are basically specialized programming languages. So let's take a look at both sides now. So roughly speaking, the Dolev-Yao approach focuses more on the protocol core, which leads to more abstract models that can be analyzed in a mostly automated manner. This approach makes it easier to analyze security properties that require a global view, for example, forward secrecy, because it analyzes the whole protocol and all its possible execution traces at once. At the same time, this all-at-once analysis usually requires bounds on data structures and bounds on loops. Dolev-Yao style tools also support equational theories. Now, on the other hand, the dependent type approach focuses more on implementation aspects, which leads to modular proofs that are usually local to single functions. In turn, this means that there is no global view, which makes it hard or even impossible to state and prove properties like forward secrecy. The models are written in specialized programming languages, and therefore the analysis takes place at the implementation level, and models are not restricted in using unbounded structures and loops. And for the same reason, the models are usually executable and can even be interoperable with other protocol implementations. But in many cases, dependent type analyses require monotonic state and more user interaction to prove properties. So, as you can see, both approaches have their strengths and weaknesses, and we want to combine their strengths. And this is where DY star comes into play. So let me go to that slide again. And here, yes. So DY star bridges the gap between these two sides. And we built DY star on top of the F star programming language, which is a fully fledged programming language aimed at program verification. So to ease the proof burden for the user, F star relies on a SMT solver to discharge proof obligations, and by this providing a good amount of proof automation. So let's take a look at how DY star has been used so far. We use DY star to model and analyze the signal messaging protocol, which is used in popular messaging applications and thus by billions of people. Leveraging the strengths of DY star, our analysis of the signal protocol is the first to account for an unbounded number of rounds of the ratcheting sub-protocol, and at the same time, proving global security properties like forward secrecy and post-compromise security. A second case study is our analysis of the ACME protocol. This protocol is used to automatically issue TLS certificates, and the most prominent user is probably Let's Encrypt, which has issued well over 1 billion certificates so far. So our analysis features a very precise and detailed model of the ACME protocol, comprising more than 16,000 lines of code, which makes it one of the largest and most in-depth analysis in literature. In fact, our model is so detailed that by using our client model as an application layer library, we can obtain valid TLS certificates from Let's Encrypt. In addition, we also modeled and analyzed a small set of standard protocols, namely NITEM Schröder-Löw, ISO-DH, and ISO-CHEM. So with F star being new, there is lots of interesting work to be done. For example, we want to implement the web infrastructure model on top of DY star. The web infrastructure model is the most detailed formal model of the web and was successfully used for many analyses so far. We also plan on extending DY star with equivalence properties and computational analysis capabilities. So before I conclude, 2 more remarks. There will be more about tool-based protocol analysis in the invited talk tomorrow by Karthik Bhagavan. And also, if you're interested in this work, our group in Stuttgart is looking for PhD students and postdocs. For more information, please visit our website, and thank you very much for joining.
Thank you very much, Pedram. Thank you for your wonderful talk and finishing before time. So let's move to our next speaker. Our next speaker is Mohammad Usama Sardar from Technic University of Dresden, Germany. So over to you, Mohammad.
Yeah, thank you. So this talk is related to the CCC white paper, and if you have been following the ISER conferences, you might know about the 3 episodes that we have already discussed. If not, I will like to just remind you or give an overview of what we saw in the last 3 episodes. So in the first and second episode, we talked about what Confidential Computing Consortium has in its white paper as the claims, which is one of them is mentioned here. Unlike the term confidential computing, several of the terms used in the diagram have multiple competing definitions. And if you see the diagram referred here is this one, which I replicated here. The first claim is that there is a unique definition of confidential computing, which we already clarified that it's not the case. And secondly, also that the competing definitions of other terms, including homomorphic encryption and multi-party computation, was the part of episode 1 and 2. So what we saw in the episode 3 was that there are other vague and incomplete definitions of trusted execution environments in the white paper, and also some weird terms like trusted execution environments, which don't make much sense. And there was, so the definition of confidential computing itself was based on hardware-based trusted execution environments. And the term itself was not clearly defined what actually distinguishes a hardware-based trusted execution environment from a software-based trusted execution environment. So now we proceed with the new part of, or the 4th episode, which is talking about the programmability. Here in the diagram, you see this part, programmable. So one of the 2 definitions by the consortium, which actually contradict, was based on this programmability. And what they define or talk about, describe programmability is that some trusted execution environments may be programmable with arbitrary code, while some may only support a limited set of operations. And this sentence has no clarification whether the definition of programmable here or this set actually is meant to be this programmability with arbitrary code, or secondly, the possible possible interpretation on the other end is that this this part with the limited set of operations, is this also going to be considered as programmable? So there are at least these 2 interpretations and a number of interpretations in between that what exactly is the programmability. So, and for completeness, we have a set of programmability here. It should also be shown in the software trusted execution environments. Attestation is one of the most important processes of confidential computing. And what the consortium defines is attestation is the process by which one party called a verifier assesses the trustworthiness of a potentially untrusted peer, that is the attester. It's not clear here what exactly trustworthiness means, and it's really important to clarify that the most important or the core property of attestation is measurement, which actually is not visible from the definition itself. And then attestation, as I said, is a core part of confidential computing. The reason being that as opposed to fully homomorphic encryption and multi-party computation or other solutions, here in confidential computing, we need to trust the hardware and at least one layer of the software stack. And therefore, there is a greater need for remote attestation in this case. And without attestation, confidential computing itself is incomplete. I mean, it's the core part of confidential computing. It's computing without attestation is no better than any conventional computing solution paradigms. The reason being the remote user cannot distinguish a malicious platform from a genuine one. This is the property which actually helps establish this trust. And even with alternatives of attestation, for example, authentication process, even if you have that, that is insufficient. What we find really comic is that the consortium itself kind of acknowledges the importance of attestation by saying that any attack that would compromise the attestation of a TE instance could lead to a workload or data being compromised in turn. However, this does not replicate in the definition of confidential computing. And this is our one of the major concerns, and we find it incomplete definition of confidential computing without having an explicit mention of attestation process in the definition. So that's what we claim, that attestation should be really a part of the definition of the confidential computing. So these are the references which have been used in this presentation, and I thank you all for your attention, and I hope to see you in the next episode, where I will describe in detail about the comparison done by the Confidential Computing Consortium of the confidential computing with the homomorphic encryption and TPM-like technologies. And there I will describe the problems in the comparison and the survey they did. Thank you very much, and hope to see you in the next episode.
Thank you, Mohammed. Thank you very much for this wonderful talk. And again, finishing on the time. So our next speaker would be Jyotirmoy Pramanik from Taki Government College. So Jyotirmoy, over to you.
Okay. Am I audible as well as my slide is visible, right?
Yeah, absolutely.
Okay, thank you.
Go on.
So welcome. I welcome every one of you. And this talk is about something called the cost of sharing a secret. And there is already an existing notion of a share size in secret sharing. And I will be coming to what a cost means in sharing a secret. So secret sharing achieves something as follows. Suppose you have a very sensitive or dangerous piece of information that is something which you don't want to fall into hands of your competitors or enemies. So what you do is you split the piece of information into certain parts, maybe finite, or according to some recent works, maybe infinite number of parts, in a way that only some qualified combinations of those parts or shares are able to reconstruct your secret back, whereas every other combination, which we will be calling as forbidden sets or forbidden combinations, those are unable to reconstruct the secret back. So the formal definition of these properties are as follows. We call it the privacy property, that any forbidden collection of shares gives you nothing that is already not derivable from the distribution of the secret space itself. And there is something called the correctness property, which says that even if a qualified set pools its shares, you will be getting the entire secret back. And the idea is as follows. There is a space of secrets, and there is a special participant called the dealer. What he does, he generates few spaces which look random from the point of view of outsiders, and values from these spaces, called the share spaces, will be given to the participating people or the shareholders. And the notion is that the ith participant will be getting a share size of some value, which is the cardinality of the ith share space. Now, motivation behind this work is, from an implementation point of view, that we might need a prior budgeting of the work to be done. And this is very clearly visible in the case of kn threshold secret sharing, where k is a very small threshold compared to the total number of participants involved. You may think it as a 2n or maybe some other lesser valued thresholds. And also there is the notion of flexibility in case of malicious adversaries in secret sharing, which sort of invokes this work. So what we do is nothing very unimaginable. We just consider the union of all such share spaces and consider the cardinality of that union set as the cost of a secret sharing. Now, this very little change is going to address the problems that I mentioned earlier. And here are some immediate observations. That in case of ideal secret sharing, we know that the share of size is as same as the share of the secret, and in case there is n participants involved, this changes. And in case of ramp secret sharing, we know the share size is lesser than the share of secret, and whenever we are dealing with malicious adversaries, the share size is known to be greater than the size of secret. And there are some other notions such as evolving and hybrid of these notions as well. And the notion of flexibility is something as follows, that if the security parameter in a secret sharing scheme is independent of the secret size, then the secret sharing is said to have flexibility. Now, it can be observed in the following schemes that these schemes have flexibility, and accordingly, the cost of the secret sharing is listed in the third column. And of course, in some cases, it is difficult, and we need to set parameters. We need to set bounds and parameters according to the secret sharing scheme, and these areas are still open. And there is a recent notion of almost semi-honest model where, in case of infinite number of shareholders involved, every participant will be able to test whether the participants arriving before him or her are submitting correct shares or not during the reconstruction of the secret. So in this model, it is still open whether what can be the cost of secrets and all, and in case of hybrid secret sharings as well. And these are some open directions that may be explored. Thank you.
Thanks, Jyotirma. Thanks for this wonderful talk and really wonderful slides. So let's move to our next talk. So the next talk would be by Chandon Goswami from Presidency University. So Chandon, over to you. Can you share your slide? Chandon, can you share your slides? Chandon, can you hear us?
Yes. Yes.
Okay, sure.
So can you help me share my screen? I'm not able to share my screen.
Can you click on the sharing screens?
Yes, sir. Next.
Then I mean, share the whole screen or the whole application.
Chandon, is that a presentation or a movie?
Yes, presentation.
Or have you saved it on the desktop?
Hello, everyone. First of all, I'd like to thank all organizers of Indocrypt 2021 for giving me the opportunity to deliver my presentation. So, my title of my presentation is KP distribution scheme for IoT devices with enhanced resiliency. So first I introduce IoT. So what is IoT? IoT, we all know that IoT is Internet of Things. And next, we can see that in the meantime, Internet of Things, all devices connect via Internet of Things. But in the worldwide, connected IoT devices are grown exponentially. Since the IoT has a lot of applications, it's very important to understand the security aspect of it. In case of attack from any adversary, things might go very wrong. So my target is to give a security aspect of IoT devices via mathematical point of view. So for that, we want to roll up the cryptography, and the cryptography is only as good as the security of keys. So secure management of keys describe the entire life cycle of keys, and the keys must be pre-distributed before deployment. But uploading them to the devices due to the lack of a secure mechanism for key distribution during communication, and the combinatorial designs application in KP distribution has been considered as a suitable method due to the low overhead in the shared key discovery phase. Generally, public key mechanism involve huge computational costs. So for limitation on computational capabilities and the storage capacity, symmetric key mechanism are preferred. Next, I define how the security or privacy preserved in the IoT device via an parameter resiliency. So resiliency is the ability of a network to continue to operate it in presence of compromised nodes, and the amount of resiliency indicates how many network connections are uncompromised by capturing the number of IoT devices. So from this point of view, I introduce and how hash function are role in the security aspect of IoT devices. Here we see that if here 4 nodes, that means 4 devices, device number 1, number 2, number 9, and number 6. And the 2 device 9 and 6 communicate via the key K5. And the number of device 1 and device number 6 is communicated with K5. So if any adversary or attacker capture the key K5, then he break the link between the devices number 9 and devices 6, as also as the devices number 1 and the devices number 6. But if we add the keys of hash power, then we see that here this picture that if any attacker compromise the link between the device number 9 and device number 6, but he cannot break up the link between the device number 1 and the device number 6, because we all know the property of hash function. So next I introduce my scheme. This scheme is base scheme. So base scheme basically an KP distribution scheme, deterministic KP distribution scheme. Here the number of nodes is n choose 2, and the total number of nodes is n choose 2, and the number of keys of each node is 2 into n minus 2. So here put an example for n equals to 7, so 21 many nodes, and we consider all members of the ith row of the matrix as the members of the ith group, and any 2 group number of elements of common elements of any 2 group is 1. And for that I describe the key construction of the base scheme. So for any node between the total number of nodes, then we can find in mathematical way that the number of nodes of any number of keys of any 2 nodes is 2 into n minus 2. So here for n equals to 7, so here the node ID is 15, and the total number of nodes is 21, and number of keys of each node is 10. So basically now we find the common keys of 2 nodes. The number of common keys between any 2 pair of nodes is either 4 or n minus 2, now given two nodes I and j, and let us try to find the structure of the common keys. So let us assume the keys I and j, and there are 4 possibilities. So total number of common keys between two nodes either 4 or n-2. Next, we construct base scheme to base subset scheme. Here, for an example, n equals to 7. So for depth 1, total number of nodes 21, and the number of nodes create from each node is the total number of keys. So we already see that the total number of keys of each node is 10. So from any node in depth 1, the total number of nodes create is 10, and depth 3 and total number of nodes each create is 9. As we already told that the number of keys of each depth is decreased by the cardinality of 1. Next, I introduce the bidirectional hash chain for base scheme subset. As an improvement to the gain of better resiliency, we use the bidirectional hash chain of base subset. In such a case, the structure of the keys in the key ring of a node is the triple coordinate, and this used via hash function. And now we already see the FLS is the resiliency parameter introduced the all of the previous paper, and the lesser value of FLS give the better resiliency. But we introduce a new resiliency parameter TS, and TS is the average value of the probability of two non-restricted nodes to compromise all the links between A and B. So this is an where TS is.
Chandon, can you quickly wrap it up?
Yeah. So FLS is the proportion of two numbers CS and L. CS is the number of links comprised of the uncompromised nodes upon compromise of X random nodes, and it is the total number of links in the original network. But we introduce a new resiliency parameter, capital TS. So for capital TS, we introduce TABS. For TABS, for two secure connected target nodes A and B, and for a given value of S, TABS measures the probability of finding S many non-restricted nodes to compromise all the links between A and B. Here, script n is the number of nodes in the network, and the target nodes are the two nodes which communication and attacker is trying to break. So capital TS is defined the TABS summation of all TBS over all the pair of two target nodes, and proportion to script n in n minus script n minus 1. So from the definition of TS, first trace all nodes which compromise leads to capture all links between a pair of.
Can you quickly wrap it up? Just.
So this is the experimental graph.
Okay, great. Thank you very much for your presentation. And so we move to the last talk of this RAM session. So Dr. Talari, are you there? Dr. Talari?
He is there backstage, but his video and audio are both muted.
Dr. Talari, can you unmute yourself? Dr. Talari, can you unmute yourself?
So no contact number with me as well. So
And thank you very much for Professor Adhikari, Professor Prinil, and Professor Carsters for giving.
thanks everybody. Yeah, so it's really enjoyable 5 minutes talk.
So thank you very much, everybody. It was a great session. See you all tomorrow.
See you all tomorrow then. Yeah,
Bye-bye.
It was really a quite enjoyable session. We had 7 speakers. All of them performed really well. I'm not sure who is going to send their papers to cryptology, but surely we enjoyed all. Thank you. Thank you very much. Okay, then see you tomorrow.
Thank you very much. Bye-bye.
Bye-bye.